The second lesson in our unit on field forces is on how we calculate gravitational forces. We just have one learning target for this unit, and that is to be able to use Newton's law of universal gravitation to calculate the gravitational force acting between any objects. So, a little review from our first lesson on Newton's law of universal gravitation. Ask yourself, and pause the video, what is Newton's law of universal gravitation? You might recall that Newton's law of universal gravitation tells us that all objects in the universe attract all other objects in the universe by the force of gravity. And also recall that there are two factors that affect this force of gravity. Again, pause the video and ask yourself, what are those factors? Hopefully you have come up with the two factors that affect the force of gravity. If you recall correctly, those two factors are mass and distance. In other words, the mass of the two objects and the distance between them. What we want to examine now is what is the quantitative relationship? In other words, how much do mass and distance affect this force of gravity? Or in other words, how do we calculate it? So, Newton's law of universal gravitation. We can calculate the force of gravity acting between two objects by using the equation that I'm going to show you here. Now here's the equation. This is another way of stating Newton's law of universal gravitation through this equation. Now at first glance you might think, oh my gosh, this equation looks very difficult. There's all sorts of letters and numbers and there's a negative sign in there. How do we do this? Well, it's really not that bad. And I'm going to walk you through this step by step so you understand very easily how to use this equation. So first of all, we need to understand what each of the symbols mean. So here's our equation. You can see it here. We have F sub g, with the subscript g there, equals negative capital G times m1 m2 over d squared. That seems really complicated, but as we said, it's really not that bad. So Fg simply means the force of gravity. Okay, Fg stands for the force of gravity. So we're saying the force of gravity between two objects equals, and then we use the equation. Capital G is a constant. It's called Newton's gravitation constant or Newton's gravitational constant. And there is a value for it. And here is the value for Newton's gravitational constant. This is not a number that you need to remember. You will always be given this on any sort of assessment. So again, you don't need to memorize it. But do go ahead and take a look at it here. Notice the value. We have 6.67 times 10 to the negative 11th. And then the units on it are what are kind of confusing. Newtons times meters squared per kilogram squared. It seems like a very funny unit, but once we start doing the calculations, you'll see why it has those units. And again, you do not need to memorize this value. This is something you will always be given. All right, so that's the capital G. M1 and M2. Well, M stands for mass. So M1 is the mass of the first object, and M2 would be the mass of the second object that we're calculating the gravitational force for. And then D is the distance between the objects. And so if we're given all these values, if we're given the mass of the two objects, M1 and M2, if we're given the distance between them, and G will never need to, well, you'll always be given it, meaning you won't need to memorize it, but you won't ever have to look up something different because it's always the same thing because it's a constant. Given those three things, you can calculate the force of gravity acting between the objects. So let's just break down each part of this equation here. So the capital letter G, as we saw on the previous slide, that's Newton's gravitational constant, and there's the value as we mentioned. Notice it's a really, really small number. Now I know you've learned about scientific notation in a little bit in your math classes, and we've probably talked a little bit about it in this physics class. Notice the exponent, 10 to the negative 11th. That's a really small number. So in other words, if you were to write this in standard notation, you would need to move the decimal point 11 places to the left. So that would be 0.0000000000667. If you didn't catch that, that was 10 zeros and then 667. In other words, what we're saying here is gravity is actually a really weak force. It's actually a very weak force. Now you might think there's no way it's a weak force. It's really strong. We can't jump off the earth. Gravity is very real to us. Well, the only reason that we can experience it so easily on Earth is because it takes a huge mass to notice gravity. And obviously the Earth is very massive. And so that large mass of the Earth is what allows gravity to affect our lives so greatly because of that huge mass. If the Earth was much less massive, there would be much less gravity on Earth. So M1 and M2, as we saw in the last slide, those are the masses of the objects. And just a couple things about this. Whenever you use this equation, you need to make sure your mass units are in kilograms. Okay, they need to be in kilograms. And the reason why that is because of the unit in Newton's gravitation constant. Notice in the denominator, the unit there is kilograms squared. So if both of these mass units are in kilograms, what will happen is they'll actually cancel with those kilograms in the gravitation constant. Now, thinking about what we learned in our last lesson on gravity, recall we said that gravity is stronger whenever the masses of the objects are larger. And here we can see why. Notice that the masses, both M1 and M2, are in the numerator of the equation. So if either M1 or M2 are larger, then the effect is going to be the gravitational force, Fg, will also be larger. So as we have already learned, greater mass means greater gravity, and we can see that in the equation. All right, the last term there in the equation, that d squared, okay, that is the square of the distance between the objects. So I'm not just dividing by the distance, I'm dividing by the square of the distance. Recall from math, when you square something, that means you multiply it by itself. We always want our units on that distance to be in meters, and that's for the same reason we said the masses need to be in kilograms. If we look at our units on the gravitation constant, notice it's Newton meters squared. So we want that distance to be in meters because that will end up canceling with the meters in the constant there. And then again, think about what we learned about gravity and distance in our last lesson. And you might recall that we said that if objects get farther apart, that weakens the gravitational force between them. And here we can see why that is. If d gets bigger, and again notice the distance is in the denominator here, if d gets bigger, that means we are dividing by a bigger number. So that's going to in turn make the gravitational force between the objects smaller. And that, recall, is exactly what we said in our first lesson on gravity. Greater distance, less gravity. All right, now that we've examined that equation, let's take a look at how we actually use it to calculate the gravitational force between objects. So here's our situation. It says calculate the force of gravity acting on a 65 kilogram person standing on the surface of the Earth. Earth's mass is 6 times 10 to the 24th kilograms and has a radius of 6.4 times 10 to the 6th meters. So we need to use this equation here. The Fg equals negative g times m1 m2 over d squared. Man, see, it's really complicated, I know, but it's really not too bad. But before we actually plug any numbers into this, I want you to consider something. Why are we told the radius of the Earth? We're told that we're standing on the surface of the Earth. Why do I need to know the radius of the Earth? Well, let's just picture the situation here. I'm going to draw out a little picture. So here's our Earth, and then here's the person standing on the Earth. And I know you might say, well, that person's huge compared to the Earth relative to what it should be. Yeah, I know. It's not to scale. That's okay. Well, the reason we need to know the radius of the Earth is in this equation for calculating the force of gravity, this d, the distance between the objects. You might say, well, it's 0. The person is standing on the Earth. There's no distance between them. Well, that distance actually refers to the distance between the centers of masses of the two objects, or basically the middle of the two objects. So when we talk about someone standing on the Earth, we need to know the radius of the Earth to figure out how far the person is away from the middle of the Earth. So remember radius from your math classes, that's the distance from the middle of a circle to its edge. And for the Earth, that is 6.4 times 10 to the 6th meters. And so that will be our distance term that we plug into our equation here. All right, so let's actually go ahead and see how the equation works here. So here's that same problem again. Didn't change any of the words in it. And here's the equation we're going to use. At this point, it's just a matter of plugging in numbers. You might be thinking, uh-oh, we're missing something. We don't have a number in here for the capital G, that gravitation constant. Well, you don't actually have to be given that in the problem. You'll always be given that on the assessment if you need it. That's a constant. So at this point, we're just going to plug in numbers. So notice Fg equals the negative of the universal gravitation constant, and that's 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And again, that's the number that you don't need to memorize. You'll always be given that. Whenever you get a worksheet or something on this, you'll just want to write that right on there. You don't have to keep looking for it. Now we need to multiply by m1 and m2. Well, those are just the masses of the objects. In this case, our two objects are the person. Then the person has a mass of 65 kilograms. And then the Earth, which has a mass of 6 times 10 to the 24th kilograms. So I have 65 kilograms times 6 times 10 to the 24th kilograms. And then we're going to divide by the square. Again, notice it's a square of the distance between them. And recall, this is why we needed the radius of the Earth. So this is that 6.4 times 10 to the 6 meters, because that's how far the person is from the center of the Earth. And then notice here, we're squaring that. We're squaring that. Now, usually the hardest part of this whole problem is getting it plugged into your calculator correctly. This is why we took the time in class to go through how to use the scientific notation feature in your calculator. So make sure you're using that whenever you plug this in. In fact, go ahead and pause the video and plug all this into your calculator and see if you can get the right answer here. So you plug this stuff into your calculator. The answer I get is a negative 635 newtons. Okay, and notice the negative here out front. We'll talk about that in just a second. Now, your calculator is not going to tell you exactly negative 635. It's 634 or 635 point something. I've just rounded it to 635. If you have plugged all this into your calculator and you get something that looks like 635, excuse me, negative 635, then you did it correctly. If you get something that's way different, maybe something like 6.3 times 10 to the 18th or 6.3 times 10 to the negative 34th or anything along those lines, then you did plug it in incorrectly and you want to go back and try that again. Now, last thing here, what about this negative sign? What does that mean? The force of gravity is negative. That doesn't seem to make sense. Well, there's a convention that's often used in physics, and the convention is this. A negative force will represent attractive forces. So when we say the gravitational force is negative between this person and the Earth, that means the force is attracting them to each other, which we are well aware of is always the case with gravity. We know gravity is an attractive force. Here's another example. It says, use the following data to calculate the force of gravity acting on the same 65 kilogram person standing on Earth by the sun. So now, instead of calculating the gravitational force between the Earth and the person, we're going to calculate the gravitational force between the sun and the person. And notice here we're given the data on the mass of the sun and the distance to the sun from the Earth. All right, so it's the same equation we just used. The force of gravity is equal to that negative g times m1, m2 over the distance squared. Just a matter of substituting in our numbers. So once again, negative, and then gravitational constant is that same 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. And then our mass for the person is still that same 65 kilograms. And then our mass for the sun now, this is obviously different than the mass of the Earth. That's the 2 times 10 to the 30th kilograms. And then we're dividing by the distance squared between the Earth and the sun. Or in this case, the person and the sun, which would be virtually the same. So that's 1.5 times 10 to the 11th meters. And then we square that. Now, one thing I failed to discuss on the last slide, and I kind of meant to leave it for this slide anyway, just to let us focus on the calculations on the last slide. So let's talk about our units here. So notice our units here. I have a kilograms times a kilograms here for my masses, but then I have a kilogram squared in the denominator of that constant. So those are actually going to cancel. Okay, that kilograms squared will cancel both of these kilograms here. And then that is the same story for the meters. Notice I have meters squared in the numerator here, then I have meters squared in the denominator here, so they cancel. So the only unit we're left with is newtons, which we are well aware of as a unit for force. So we plug all this in, and again, go ahead and pause the video, practice plugging this in your calculator, make sure you can do it correctly. The value I get for this force is a negative 0.385 newtons. Now consider that compared to what we calculated on the previous slide. Remember, the previous slide was negative 635 newtons, so way more force. And we would expect that. The force attracting this person to the Earth should be much greater than attracting them to the sun, because we're way, way, way closer to the Earth. Even though the sun is much more massive, we're so much closer to the Earth that gravitational force should be much greater. All right, just a couple of review questions here based on what you have seen and listened to so far on this video. First question, write the equation for Newton's law of universal gravitation and indicate what each variable stands for. So pause the video, go ahead and do that. All right, you've already seen this equation a few times. You've probably written it in your notes a few times. The equation for Newton's law of universal gravitation is Fg equals the negative g times m1 m2 over d squared. So we can see Fg there equals negative g times m1 m2 over d squared. And one comment I should make here, much like that universal constant, gravitation constant g, you do not need to memorize this equation. This would always be something that would be given to you, although some of you might already have it memorized just because you've written it down a few times. But again, you don't need to worry about memorizing it. Now, what is important, though, for you to know and to have memorized is what each of these variables mean. And that's what that second part of the question is. When Fg is the force of gravity, capital G is Newton's gravitation constant, m1 and m2 are the object's masses, and d is the distance between the objects. All right, and one more question here. This is just a calculation. It says, use the data below to calculate the gravitational force between the Earth and the Moon. So now we're talking about the force pulling the Moon and the Earth towards each other. And notice we're given the mass of the Earth, the mass of the Moon, and the distance from the Earth to the Moon. So again, pause the video, try this yourself, and then play it once you've done that. So calculating gravitational force between objects, we know we're going to use Newton's law of universal gravitation, the equation. So that's the Fg equals negative g times m1 m2 over d squared. At this point, it's a matter of substituting in some numbers. So negative 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Recall that's the constant value that you do not need to memorize. You'll always be given that. And then plugging in our numbers here, the mass of the Earth, 6 times 10 to the 24th kilograms, times the mass of the Moon, 7.3 times 10 to the 22nd kilograms, divided by the square of the distance between them, so 3.84 times 10 to the 8th meters squared. And if you haven't already, go ahead and plug this into your calculator, see if you can get the right answer. The answer I get is negative 1.98 times 10 to the 20th newtons. Now notice how large this value is compared to the values we've seen in the examples earlier in the video when we were calculating the gravitational force between, say, the person and the Earth or the person and the sun. Why do you think this is so much bigger? Go ahead and pause the video and jot down a few thoughts on that. Why you think this gravitational force here is so much bigger? So you've had a chance to think about this for a second. The reason it's so much bigger is the masses of the two objects that are involved. Before we were calculating the gravitational force between a person and either the Earth or the sun. Well, now we're calculating the gravitational force between the Earth and the Moon. Now, obviously, the Moon is way more massive than a person would be, so that's what makes this so much larger. Even though, obviously, the Moon is a lot farther away from the Earth than the person would be, the extra mass just makes it so that the gravitational force has to be so much larger. Also consider this: if we know that the Moon is in orbit around the Earth, and the force that's going to allow that to happen has to be ginormous, has to be really, really big. And so that certainly coincides with the values that we have calculated here. All right, in this video, we have only had the one learning target. We've used Newton's law of universal gravitation to calculate the gravitational force acting between objects. We looked at the equation very carefully, examined each of the variables on there. Again, recall that you do not need to memorize that equation. That's something you'll always be given, but we do need to be able to use it appropriately. And maybe the most difficult part of all this, recall, was getting it plugged into your calculator correctly. So do practice that because it will be important for you to be able to do.